Today, I come to speak to you of a future of change. Change management, or not just change management, but of the world, of the internet, of our industry. I talk about changing not just the future, but managing the changes of the things to come. I consider myself a visionary. I've been building wearable computers since 2000, selling PaaS services since 2002, building VM-based VPS services and cloud services since 2006 and 2007, doing services such as similar to Linode and SliceHost and competing at prices that nobody else could. I've been an OpenStack contributor since 2011, and since January, I've been working at Docker. Today, you're probably configuring and managing servers, VMs, perhaps containers. You might also manage network infrastructure. But whether you are managing physical servers, virtual ones, or both, if you're here today, you're probably using configuration management tools or planning to use them in your organization. Today, these solutions primarily look like are provided by a configuration management service, which provides a configuration matrix of recipes and manifests. Servers they boot, they connect on the network, they subscribe to this service, and then they try and reconcile their state with the canonical state that it should be according to these recipes in these manifests. And these systems thus place an emphasis on idempotency. If you're really savvy, these machines might boot into a set of pre-configured images. You might use Chef Zero, Chef Solo, Puppetless, Masterless Puppet, but they all largely follow the same paradigm. Oh, not that one. One of my problems with these tools is that they are overly complex. The fact that idempotency is a concern in the design tenet only highlights the legacy that is encapsulated in these products. It isn't that idempotency is bad necessarily, but it presumes that we might ever run something twice, and that we're willing to disregard the state of the system prior to running the configuration management the second time. In fact, a design tenet should be that we never allow running configuration management twice, that our provisioning is worm. Write once, read many. We use configuration management to build an artifact, and we use that artifact to boot our images. That's one way of expressing what's now being called immutable infrastructure. Are we managing configurations, or are we managing systems? And is there a difference? Systems configuration and management are really indistinguishable. The easiest way to enable worm-based provisioning today is to use containers. And this is one of the reasons, amongst several, why people are seeing containers as a solution to their problems today. But as you've probably heard, containers are coming. And you'll notice I haven't used the D word once, except maybe for where I'm working. But it's happening, right? Containers are happening. It's been happening for a long time. Whereas Docker is new, there it is. Containers are not. They have been around for well over a decade now. We've had OpenVZ and Parallels and these other container solutions. In fact, the original .cloud solution was built around OpenVZ. Solomon showed this to me back in 2008 when he was doing his first pitch for .cloud. And I said, this would be great when this is a tool that everybody can use and it's free to download and use and it doesn't require MongoDB and you need some PaaS experience. So after 4 or 5 years, he came back and Docker was a thing and I joined him. Anyway, so what are containers? They are just a security construct. They are not a mythological box They are not even virtualization, which employs interesting hacks around CPU interrupts and more recently processor extensions. No, they are just processors on Linux with a sprinkling of security. While the security version of the story sounds like virtualization, it isn't. Neither is it virtualization or is it like virtualization. Instead, it is a capability not unlike SELinux or AppArmor. This is why I find the questions about the security of Docker particularly interesting, because it is not a removal of any layer of the system, but the addition of one. And in fact, it's a layer that you can add above and below. So you can add it underneath of VMs and inside of VMs. It is the addition of constraints on processes that were not there before. However, what is disruptive is this newfound portability and transportability of these containers. What we have done is not to containerize processes on a host, but to enable self-contained application images to become portable between systems. Portability and transportability is one of the key values that Docker Engine adds to containers. Of course, containers are not a replacement for configuration management. The fact that they simply enable worm-based provisioning reduces, or in some cases eliminates, the need for other configuration management tools in the provisioning chain. However, there remains a need to manage that change. It's not just about securing your processes in a container, although that's part of it. And it's not just about portability. It's about the portability of the services that run within them. Containers are a single part of a wider paradigm shift away from servers. When we view our applications as running on a platform rather than running on servers, it is not hard to see the writing on the wall that our operating system is dead. Now, this might appear overly dramatic. However, look at the new container-specific operating systems, such as Boot to Docker, CoreOS, and Project Atomic, which is Red Hat's new operating system. We can bring up a kernel running Docker, and Docker runs self-contained applications that are built from traditional distributions, but are not actually running those distributions. Instead, they build an image based on a distribution and run a single process from it instead of a init. Now, granted, you can run an init in it if you want to, but the microservices model is you just run that process. In the container microservices model, the application runs in a container and only uses shared libraries or possibly uses the packages for the application service itself, and less commonly uses the distribution's binaries, right? So all of these facilities, all of these tools, all of these packages that are in your distributions today are not used in containers, right? It's just the libraries and binaries that your application itself needs. 2 years ago, I said to a colleague, the kernel is dying. But now, I fear the distribution is dying. But what we're really doing here is we're following a trend of thinning the fat. 2 years ago, when I spoke of the kernel dying, I was referring to Linux in the sense that it was time for it to fast and to tighten its belt. That with virtualization supporting a homogeny of hardware, our kernel would become thinner, and in a sense that may still prove true. But what is currently happening is that Linux as a kernel is, in a way, becoming resurgent. Containers mean that the kernel is relevant again. The kernel is not just a place to manage hardware drivers, but a layer of protection for your applications. Without the kernel, applications would be protected by nothing but their hardware or their VM, and would be absent in controls offered by SELinux AppArmor, and C groups. Interpreted and bytecode languages such as Python, Ruby, and Java suddenly have advantages to running on Linux, whereas a couple years ago, the greatest friction to leaving Linux was the lack of choices and poor support for FreeBSD and other BSDs on various clouds. We're increasingly entering an age, entering or re-entering an age where the friction of leaving Linux will be based upon the capabilities of the kernel and the platform itself. Because containers finally leverage the things the kernel does well. With changes in how people use Linux, with virtualization and containers, Linux will continue to change to these paradigms. While there will always be someone wanting their unique driver in the kernel, the number of drivers that people will use in production and those that ship with Linux are still likely to decrease. This will only happen more as users only use Linux in virtualized environments or with containers. Honestly, my view of containers is probably a bit more forward-leaning than most. I believe the pendulum tends to sway, and we see the industry move from one side of things to another. You know, mainframes to personal computers to centralized cloud to decentralized cloud. With containers, I do expect that we may see that pendulum shift again. Between between virtualization and containers in the same way that we've seen that pendulum with para-virtualization and hardware virtualization. That what we may settle on in the end may be something that looks like hybrid containers, where we will be able to capture syscalls and have different versions of syscalls that operate differently based on whether or not we're in a container or not. Right? That these containers may become not simply C groups and not simply a construct of using the kernel, but actually may become better first-class citizens. And that we may even use some of these similar techniques to what was done in the creation of hardware virtualization. There is, of course, the matter of orchestrated per-tenant clusters which run clouds of containers, such as Google does. Right? This is an example of a hybrid solution, right? Google said we cannot run these containers securely in a multi-tenant situation without putting them in VMs. And they're right. Like, that's the way to do it, especially right now, if not always. And regardless, the point is that microservices mean compartmentalization. And with containers, means it's smaller distributions and a smaller attack surface per service. As to whether or not it reduces the total attack surface is another debate, but it certainly means smaller pieces with smaller attack surfaces per each piece, which is more manageable and easier for you to manage the change and the configuration of those. And it makes sense, really, because microservices are a misnomer. They are commoditized processes, just as virtual machines have commoditized hosts. And the great thing about commodities is they become just another thing in that big haystack. Its close alignment to the Internet of Things is a disruptive element of the microservices movement. You've probably heard by now, the Internet of Things is upon us. It is happening, but it has been happening for only a short time. It is happening, but the builders of this new world come in many shapes and sizes. Embedded software is notoriously bad, it's buggy, it's hard to manage, support, and update. We don't have configuration management for physical devices and hardware devices. But suddenly, we want to connect those devices. We've already been connecting these devices in the forms of PDUs, serial consoles, switches, and routers, as well as, I suppose, video game consoles and set-top TV boxes and these various devices. but we've done a terrible job at it. These devices are really bad. And certainly there are variants of these devices that are great, but it is the exception. Yes, and I include Cisco and Juniper in what are probably exceptions. Some of the other top-tier vendors, such as Arista, probably very good solutions. I mean, these are companies that build network devices that are core to our infrastructure, and they hire top talent to build these devices. But again, these are exceptions. The other vendors, especially the low-cost ones, has anyone ever used a good web-managed switch? Right? Anybody who's ever used those will tell you that they're not very good. People who have used SIP adapters for telephones and voice-over IP solutions will tell you that these things are not very good, even when they come from some of the better vendors. Because these problems come from the costs and constraints of the hardware, limited expertise in writing software amongst the people that are building these devices, a frequent necessity to write your own large portions of low-level stack that most high-level operating systems haven't had to write since the 70s or 80s, right? Since FreeBSD sockets became a thing, or in the 90s, if you're running Windows and DOS and WinSock became a thing, right? We haven't written these solutions. We haven't written our own TCP stacks. But that's what these embedded developers are doing, and it's broken. So it's no surprise that embedded network programming is usually bad. If most developers were working not only with 80s hardware, but with developer libraries of a similar vintage as far as networking is concerned. Undoubtedly, the best solutions prove to be the ones built on top of the most capable hardware, more capable hardware that can leverage modern software libraries. And most of that runs Linux, either via a small customized bootstrap user space or with a distribution such as Android. Even for those devices that are good, they integrate poorly with our configuration management tools, right? If we cannot manage the devices we already know and use, such as our switches and our routers, how can we manage the devices to come? For years, we've been hearing about the cloud and about cloud computing, as well as cloud this and that. But what is the cloud? It is not centralization, but rather the automation of device management. Unfortunately, the term has been overloaded to expressing any service, rather than the unique automation of physical and virtual devices as it originated. If we accept that the term has changed, and I think most now accept that this is true, that the cloud basically means it's on the internet. However, what we don't have is the hyper-connected federated cloud of devices. Right? This is the new internet paradigm, the one of connected devices, services, and automation. This is what we must build. This is what it seems is to come. This is the new cloud, and this is the cloud that I changed my slides around. So how do we talk about if things should change? So state changes, right? We like to pretend that it doesn't. The concept of immutable infrastructure is terribly broken at worst and a misnomer at best. It's true that Docker images, for instance, as I said earlier, are worm media. However, the containers themselves operate on a read-write copy. However, even if the disks were read-only, the memory would still be mutable. That is to say, there would still be state. I am sorry that this transition was horrible. And there is no such thing as stateless. Because immutable infrastructure and 12-factor do not kill the chaos monkey. The reality is that while little in the universe is static, we like to treat things as constants. We want immutable infrastructure. We want 12-factor to be a real thing. But to create images and disregard their changes doesn't work. We cannot prevent state from changing. We cannot kill the chaos monkey. Often infrastructure fails, and we do not want to tear it down. We do not only wish to preserve it, but we must preserve it. For years, I've been building systems with disposable units of compute, right? This magical 12-factor or immutable infrastructure that we can bring up VMs or we can bring up hardware, and we don't care if it dies. And it's a fallacy. Because it's naive to think we can simply throw away VMs or containers. We want to preserve their actual state for archival and analysis, and as much as possible. In fact, this is one of the properties of VMs that currently makes them better than containers. The ability to easily and affordably snapshot memory as an artifact. Now, this is not to say we cannot do that with containers, but that memory snapshots and suspended disk features are more mature virtualization technologies than they are for arbitrary Linux processes. There is something called CRAU, which can do this, but I bet if I asked anybody in the room if they've ever used it, I may get one hand, and maybe not even that. So if anyone is still questioning the value of memory and disk artifacts for your stateless containers, think about a system where your response to a security incident is to shut down your hosts, your VMs, or your containers. With a fully and truly immutable infrastructure where we presume there is no local state ever worth saving, you have discarded your application memory and possibly even your disk contents with valuable information for incident investigation. Thus, state is an essential part of your security story, and absolutely stateless infrastructure cannot be a part of any serious security story. Right? Again, the biggest problem with blind adherence to immutable infrastructure and 12-factor is the ignorance of the importance of the implicit state of a system, which should not be deemed disposable. And I'm not saying you need to abandon immutable infrastructure or 12-factor and say that, oh, I'm not going to use these things, I'm not going to believe in these. I'm saying that they are models that may not be complete and cannot be used as a basis, and may be used as a basis for your infrastructure strategy, but you may not want to use them as your infrastructure strategy, right? Take them with a grain of salt. Recognize that you cannot simply throw away your processes. Right? Because everything has state, and things are going to change. Everything is going to change. That means your servers, your VMs, your containers, and your coffee machines. In fact, my coffee machine, or my espresso machine rather, has a PID, meaning it has a temperature probe connected to a feedback loop that controls a relay. That relay regulates the heater, which controls the temperature. The machine is constantly changing temperatures, something it measures on the interval. That, of course, is state and management of that state. The Internet of Things is more than just about connecting and controlling those things. It is about sensors and the artifacts of reading those sensors. Those sensors are detecting external change and influence. They are measuring input. It is the state of those things, of those sensors. It changes, it will always change, and it is in fact the whole purpose for its existence, of the existence of that thing, right, of that device. We measure change and respond with effect to affect the state of transition we desire. And sometimes the state that changes has nothing to do with your thing, but with the knowledge that you have. We cannot control change, we can only affect it, and we can manage it. And microservices will change. Like other things, microservices expose an API. And in that API, change will happen. The state of that service will change. An API request changes a field in the database. A user logs in and a token is created. That is state change. A log file is written, etc. This is different than the implicit change, yes? If it is the explicit change that happens in a stateful service. What's amazing, however, is how well microservices map to these physical things. One takes input from sensors, the other takes input from an API. Each time, of course, we have change. Because these APIs and sensors, they both are inputs. And inputs affect change, right? Because we have functions. So really the biggest difference between microservices and physical things is that these services or these containers or VMs, that they are entirely virtual and may run on a larger physical thing, just as a physical thing may have multiple physical sensors. And of course, containers will change because containers are things. They too will change. Bit rot happens. Disks fail to make writes. Memory becomes corrupted. Out of memory, killers run. Services are attacked, and machines are compromised. And the chaos monkey lives, right? He lives in your systems. You cannot get rid of him. You cannot kill him. We need to manage containers like we manage things. Products that do not do this are not good term solutions for managing containers. In fact, what I speak of has theorems and proofs to back it up. Applying the CAP theorem, or Brewer's theorem, as it's also known, we can state this as an inability of a distributed system to provide the high availability and partition tolerance implied by immutable infrastructure and 12-factor design, while also providing the consistency necessary for reliable state management in a fully disposable manner. Purist immutable infrastructure and 12-factor design dictate stateless design. But as we know, true stateless doesn't exist. Now, the CAP theorem basically means that we cannot simply rely on logging, consensus algorithms, or other distributed computing solutions to kill the chaos monkey. What it means is that we must accept that we may lose state. In fact, what that means is that we're guaranteed to lose state. Important states such as who stole credit card numbers from your database or who took off with a copy of your private key. And we must, unfortunately, accept this. It is no surprise to me, by the way, the father of this theorem, Eric Brewer, is now the VP of infrastructure at Google, where they delivered, they're evangelizing containers technology, and he personally delivered a keynote at DockerCon, which was awesome, because I'm the whole Eric Brewer fanboy. All right, if we cannot kill the chaos monkey, we need to know how to collect its droppings. 12-factor immutable infrastructure currently fail to acknowledge this. We need to manage change, not prevent it. So, about our existing tools, right? Puppet, Chef, Ansible, Salt, and the others. Let's not fool ourselves. These tools are designed for the old paradigm. Not to say they're not useful. However, the companies that have designed and built these tools have done so often with the perspective of providing or supporting centralized infrastructure for managing provisioning. They are not designed for microservices. They are not designed for things. They are designed for creating change, not for capturing it. Some of the companies, or at least some of the engineers of those companies, have recognized the disruption. I've seen amazing effort from Chef and Salt Stack in particular toward adopting either these thoughts, if not their processes, or adapting their thoughts, if not their processes, to the disruption brought by the Internet of Things and containers. However, to be honest, I don't think that those companies necessarily need to evolve. They do something well, and it might be good enough to leave well enough alone. they might become more niche, but they have a solid market base. There are people that are still going to run enterprise computer systems and that aren't building to this new Internet of Things. There are people that are going to reuse these tools or find other purposes for them. But my fear is less that they'll fail to evolve, but they will lose their identities in the process. In fact, some of these tools are great at tasks such as scheduling and lifecycle management, even if we disregard their value for managing configuration. Furthermore, and I'll use Chef as an example because I know it best of all these solutions. Chef defines resources, which are simply objects, the Ruby objects. And these work well as abstract units that map very cleanly to the thought of managing things. One could use Chef as a cloud orchestration solution, in fact. Or rather, in fact, this was the initial scheduling solution for the Deis project, which is a containers orchestration solution. So regardless, this talk is less about the state of current tools and more about the tools that we need tomorrow, and the fact that the tools that we have today don't quite yet solve tomorrow's problems. I expect new competition to flourish around greenfield solutions for solving tomorrow's configuration management problems, and I expect the current companies, or most of them, to try and understand and figure out this disruption and to change to it. The old guard configured the interface of Linux file systems and processes, but the new guard will configure the interface of APIs. The new pattern will be to configure things through their own APIs rather than through custom agents. And the best thing is that this new fashion of configuration management will work on all things, all devices, and across all operating systems, even Windows. And we can no longer abide by configuration management tools that use or require specialized agents. Our current tools don't solve these problems. We can no longer abide these configuration management tools. We can no longer abide by SSH in particular, which is overly generic and questionably secure. And I'm sure the Ansible guys are going to love this one. And if you doubt that statement, right, how many of you blindly trust OpenSSH as we have blindly trusted OpenSSL? Why do we, how many of us have truly considered all the security aspects of OpenSSH, such as the fact that it allows negotiation of cipher types, including ARC4, which is a known vulnerable crypto system? And not to say that implementation in OpenSSH of ARC4 is particularly bad, right, or that it is exploitable, but do we really know that, right? And how much are we putting faith in these systems? So the future of management systems, and yet the current generation of web technologies, right, will make aspects of Chef server, Puppet server, Ansible, and others obsolete. If we do it right, discovery and inventory of systems, of services, and of things will be a built-in feature of that next generation technology. It will be there by default rather than the exception to the rule. Application service discovery and inventory mechanisms won't go away no more than Gopher has, right? Because remember Gopher, it was pretty cool until hypertext killed it. Because just as hypertext provided an implicit graph, linking and building relationships between websites, our next generation of web technologies will offer an explicit graph to provide discovery and inventory. Granted, it will only have an eventually consistent view of the universe because of Cap's theorem, right? But that's already true of all configuration management systems today. It's true of the World Wide Web, and according to Brewer, true of all distributed, highly available, and fault-tolerant systems. and any such system that can be built with global reach that we want to actually have online all the time, right? Because when the entire internet is down, it's such a horrible thing. So changing things, to change the things of tomorrow, we will need to use their APIs. OpenStack Heat is an interesting example of something that changes things today. It defines resources, each which may be considered as a thing, and each is managed independently and orchestrated together via their own APIs using a Heat orchestration template, which is or a hot file, right? But first, it's a good example of how compartmentalization provides flexibility, but it also highlights the complexity of managing many pieces. To solve this, Heat has what it calls provider templates. These allow creating what are effectively recipes which aggregate management of multiple things into a single resource or thing. So basically, what we found in actually building out such a system is that we now have all these little tiny pieces, but now all these really tiny pieces are even harder to manage, right? Because now that we can control and manage every piece of a distributed system, we then realize we have to bundle those things together in a way that we can manage them as an aggregate, because it's really hard to keep a developer's mindset around every one of the individual pieces, right? So unfortunately, the worst thing I have to say about Heat is that OpenStack as a whole tends to be overly insular, making the ad hoc use of components such as Heat an uncommon exercise. Still, Heat supports standalone installation. So you can use it today, you can use it to manage your things, you can use it as part of building this new generation of configuration management. It's just a little unfortunate that the OpenStack community in general is really not seeing the value that it's adding to the community and really providing it out for everybody else, right? Like their vision of Heat is that you're using it to manage OpenStack, whereas it can actually control everything in the next generation. So last week, I spoke to Jesse Robbins, a former CEO of OpsCode, now Chef, about the Chef server implementation. And it was interesting, this conversation, and I haven't confirmed it, but I'll have to take Jesse at his word. But it was my understanding from our conversation that Chef was explicitly forming a graph relationship with its nodes. In some way, Chef may already offer many of the right things for the next generation, if only at a relatively local, non-global scale, right? Like we're building these next generation technologies with patterns that we've already been using. We may just have to do them a little differently. Beyond that, Chef also manages things, similar to Heat. It defines Ruby objects that map the resources, where each resource is effectively a thing. Now, the hierarchical model is different than we might like for the Internet of Things context, but the actual recipe pattern would be surprisingly aligned should it be mapped not to local resources, but distributed ones. Of course, now you have 2 trillion problems. In a world where everything is connected, nothing is connected. When we saw computers coming, we built a hyper-connected World Wide Web. For those that remember, hyper is a word that feels so quaintly 90s or worse, archaic. But however, it is the right word for what we need today. We need hyper-connected things. We cannot afford to build networks of things that look like service-oriented architectures. There are aspects of service-oriented architecture that make sense in a hyper-connected world. Certainly, the World Wide Web terminates at web pages, which are no longer static, but those are now backed by end-tier applications. I'm not saying that we have no need for architecture in the world of things, but that, and I'll get to this in a little bit, the MQTT is not enough. The MQTT protocol, which is the MQ telemetry transport, is a lightweight pub-sub protocol built explicitly for the next generation of web technologies and the Internet of Things. I have nothing bad to say explicitly about MQTT except to say it's probably a little incomplete. And that might, in fact, be an okay thing. It does some things great. It provides a way of publishing sensor data to many clients. It provides a buffer between slow devices and fast clients. In most deployment models, it breaks out of NAT since we, as an industry, have failed to adopt IPv6. And just some more background on MQTT, beyond my notes, is that for those that aren't aware of it already, MQTT is a pub/sub protocol, but what it does that's unique is it provides caching. So what you do is you can publish a message, but publishing that message basically sets that when a request is made to that topic, and a topic, it's a messaging topic, but these messaging topics actually almost look like REST. So you construct your topics to look almost like a URL, and when you request that URL, you get back the response of whatever the value of that data structure is. But it basically, MQTT in some ways bridges the gap between message brokers and data stores, right? So it's a message queue that acts like a data store and a caching mechanism. It's actually a really great thing for the Internet of Things, right? Because these devices are slow and it buffers for you. But what it does not do is provide command, control, or configuration. It's web pool, not web control. Change and control mechanisms can be built on MQTT. It is possible, but there's no standard defined protocol for it or pattern for it. It's hard to do, and MQTT is simply not very good at it. MQTT solves important problems related to accessing sensor data, but not all of the problems of accessing and controlling things. But if MQTT is the HTML of our next generation of web, if we presume that that's true, where is our HTTP, right? Especially considering that MQTT is actually not a document, but it is a protocol, right? So things at rest. The REST pattern has been important to building modern web APIs. Those APIs are failing us. REST implies that our services are resource-centric and use a proper set of verbs for information retrieval and performing changes. The primary issue with REST is that it's not a protocol. It is at best a guideline. It is not strict enough for building a hyper-connected web. Solutions such as Waddle, Swagger, and API Blueprint seek to solve the deficiencies with REST. Yet it's not clear if they're good enough, and adoption remains key. Finally, REST implies idempotency. Idempotency as a requirement for REST is a challenge for many of the services of the Internet of Things, right? We cannot necessarily presume that machines or devices can process requests fast enough to repeat them, nor do they have the memory to provide sufficient state modeling, right? Those are the things and the reasons why people are using MQTT for the get side. But protocols such as MQTT provide value as a buffer to support idempotency for REST, right? Access to things. But this works better for retrieving data rather than creating or updating it. No, we need hyper-connected APIs because things are services and services are things. And these are your containers, your servers, your VMs, everything. So my favorite cloud is Uber. First, it makes cloud really easy to explain to the layman, but it's also really cool, right? Uber has a cloud of vehicles. Each vehicle provides a service managed by a driver. Users of the Uber cloud request resources, and Uber schedules a resource to the user, providing a service delivered by a driver. Long-term, will services such as Uber and Lyft will be powered by autonomous vehicles. Their cloud uses things to orchestrate people to provide a service. Tomorrow, it's likely they'll be orchestrating things from end to end. To build these next generation services, we need first-class events. MQTT does that well, but we need first-class command and control, right? And this is what REST currently fails to provide us. It's what HTTP itself does well, other than the fact that there's no standardization on how we do it, right? But sure, unlike MQTT, it's heavy, but change is a heavy process, right? It's the sort of thing that we only need to do on capable devices, those devices that are capable of changing and being controlled, not necessarily on your smallest microprocessors, which, by the way, are getting bigger and bigger every year, right? Every 6 months, they double. But there are other protocols as well, such as COPE, which is a lightweight protocol that translates to HTTP and is built specifically for being processed quickly and easily by low-power devices. So prototypes is what I'm coining as something similar to doc types for protocols, because protocols such as WebSockets and SPDY HTTP2 provide multiplexing of multiple channels over a singular TCP connection, right? In a sense, we might expect these to be a new sort of document type or prototype. MQTT itself is a protocol, not a document type. But if it doesn't do all the things we need, we either need a different protocol or multiple. Using SPDY or HTTP2 will allow us to provide native HTTP, COPE, MQTT, or other protocols alongside each other. Because we can either run multiple protocols over different ports, which would be horribly complex, not to mention painful, or we may decide on a single wrapper protocol. And these protocols, SPDY, HTTP2, and WebSockets, what they do is they allow simple multiplexing over a singular connection, right? They provide the capability of making your protocols, delivering your protocols as we previously delivered document types over the web. I expect that with the Internet of Things, with the large number of new nodes we expect to come online, and with IPv6, the concept of prototypes will be essential to both simplifying developer workflow as well as providing a way of traversing firewalls. Of course, every time you create a new problem, a new standard to solve a problem, you have two new problems, right? And everybody has seen this one. I can't say what the standards will be. MQTT may not be the right solution at all. Better REST may not be a solution. WebSockets or SPDY, which one is going to win, or if it's going to be a new protocol altogether. If HTTP2 ends up absorbing SPDY or not, whether or not it's a completely third thing that has to compete. It matters and it doesn't matter, right? Because all I know is that what we need is a solution to these problems, right? We don't necessarily need any of these specific solutions to the problem, right? We need to figure out which solution we want to use as an industry and adopt it, right? And to accomplish this, we need to upgrade the internet, which might sound a little bombastic, but we want to do more. We want devices to connect. We want those devices to know not just who to speak to, but how to speak to each other. Tim Berners-Lee coined the phrase semantic web, which he defines as a web of data that can be processed directly and indirectly by machines. The time of the semantic web has come. In fact, we need more than a simple semantic web. We need semantic APIs as well. So what is semantic, right? Semantics, of course, is the study of meaning. It focuses on the relationship of signifiers like words, phrases, signs, and symbols, and what they stand for, their denotation, right? And it's allowing us to understand what it is that we're talking to and what those things are and how they're relevant to us. right? Which maps so importantly to that graph of things, right? So recognizing that what we want is a semantic web, it gives us context for researching and understanding the efforts that have come before and where we are going, right? And note that I said a semantic web. I do not want to commit to any protocols or document types yet, because often when people think of the semantic web, they're thinking of the W3C's version of the semantic web, which may not be the same thing as the actual semantic web that will actually exist, right? Because standards bodies don't necessarily do the right things. And sometimes we call this Web 3.0. People have been calling it Web 3.0 for a while, right? This mythical thing that hasn't happened. We want it to happen and hasn't, right? The semantic web seems to be the next thing always on the horizon. We're always on the cusp of it, but we can never achieve it. Companies live and die by its dream. Initial efforts to build a semantic web created the Resource Description Framework, RDF, and the Web Ontology Language, OWL. And of course, these were both coupled highly to XML. In an industry that has gained disdain for XML in favor of more manageable formats and human-readable formats such as JSON and YAML, to the degree that even the W3C effectively redacted on XHTML with the publishing of HTML5. Added to these protocols have gained parlance in the common vernacular of right, so the point I'm trying to make here is that people don't even know of these protocols, right? And those that do aren't using them. And there are articles and blogs and all kinds of people discussing about how basically you shouldn't do this because nobody cares and nobody wants to use it, and there's no value to it, right? But it's the Internet of Things that gives you that value. It's the connecting of these devices. It's this next generation where we actually finally have a purpose and a use for it and not just a pipe dream. But, right, you can imagine that RDF and OWL efforts have been nearly complete failures. Of course, there are also okay, yeah, so that's what I was trying to get at. So there isn't to say the concept and model isn't right. It was simply too early. The web was not yet ready. We needed to build Web 2.0 before we could build Web 3.0. The semantic web should not just express the context of things, but provide discoverability. In fact, it has been argued that DNS already solves these problems. It is probably the largest distributed graph database out there. Yet it is flawed. DNS is critically flawed. DNS is hierarchical, which is okay, but queries are also hierarchical. With queries for record types, i.e. relationships, it is designed for a small number of relationships per node with responses returned via a single packet. Yes, one single packet. The eDNS RFC, which is an extension of the DNS protocol, which not every DNS server actually supports, by the way, allows TCP packets to be, or allows DNS packets to be arbitrarily long. Yay! But they're still in one single packet. Of course, large UDP packets are likely to just never get to their destinations, which is why eDNS allows you to use TCP packets, which will allow you to fragment those packets so that they can finally get to their destinations. But beyond that, amazingly few number of engineers seem to remember that TCP packets are limited to 64 kilobytes, right? And that's 43 fragments for each packet that has to be successfully routed at a 1500 MTU. And almost, about 3 times more of that at the minimum MTU, or minimum message segment size, which is 500 and something bytes, right? So, yet 64K ought to be enough for anybody, right? But maybe not, right? If we agree to work within these constraints, we could probably make 64 kilobytes work for a while, by using DNS as our semantic web and our semantic graph. But we're making a lot of trade-offs and hacks to make that work. And we're still, in the end, going to be limited by 64 kilobytes. And do we really want to make those hacks? Yeah, I don't think so. So instead, we probably need new, smarter protocols. It's a time for something different. There are a number of individuals and vendors alike attempting to find solutions to bridge the gap between today's protocols and tooling and tomorrow's world. Most are seeking to make it easier to build, support, and manage applications. Few of them appear to be seeking to build a global, hyper-connected web. One of the few efforts is next week's W3C's workshop on the Web of Things, because we all know how well they've done at this before. But others are working on other projects. One of those is a project called libswarm, a project that, yes, did originate at Docker, but it's something that we're working with the community and we're trying to get adoption of. And libswarm and libswarmd seek to solve the problems of providing service connectivity. It has a design such that it can be backed by services such as MQTT, and it can provide a way of discovery and connectivity of these various sites that are backed by these prototypes. So where you may have used RabbitMQT before, you would now use MQTT. And where you once used HTTP, you'd use Swarm. That is, Swarm isn't the solution. It's a Lego piece that helps build a wider solution, such as TCP and HTTP are Lego blocks and Lego pieces of the world, I guess the World Wide Web today. So libswarm actually builds on top of something else called libchan, which builds on top of existing protocols such as SPDY and HTTP2 and WebSockets in order to encapsulate other protocols such as MQTT, HTTP, and paradigms such as REST. Right? Swarm is not semantic, not yet anyway. However, it can provide an interface to semantic APIs. It's the HTTP to your hypertext. The problem is that while MQTT is semantic, it is not explicitly hyper-connected. Of course, we are, as a community, working to fix these problems. Again, this isn't to say Swarm must be the future. It is too early to pick winners. But it's not about winning the battles over protocols. It's about winning together to build a solution, not any particular solution that we've already started on, right? So if somebody in the room says, oh, we should do it this way, like make your voice heard. Because what we're trying to do is we're trying to find a solution, and we're trying to kickstart that, not force that. The key point here is collaboration and agreement on goals. So far, most or all of the other projects and efforts appear to be silos. They are not hyper-connected. They are not semantic. They are just brokers for connecting devices with no apparent aspirations beyond those humble beginnings. And again, this isn't for all of those things, right? There are a number of these solutions, and some of them may have aspirations I don't know about, right? But what we're trying to do is bridge these companies and these solutions together to build one solution. Because it's not a competition. A single canonical solution is what we need, just like we did with TCP, HTTP, and HTML. This new internet or web needs to be about things, not all devices, where all services are things and all things are services. Many of those services will be hosted by the infrastructure and services that we know and love today. We need new services and configuration management that works across all devices, clouds, and containers. We need to bet on free, open, and semantic hyper-connected protocols, whatever those end up being. Because today we are changing our servers, but tomorrow we want to change the world. Thank you. So we do have time for questions if anybody has some.
There's a microphone. Please use it so that we get your question on the recording.
Or not. Okay. Thank you.
We've got 25 minutes before break, so if anyone has any questions, now is definitely the time to ask them. So to me, the sort of the most difficult thing to wrap my mind around in all of this is moving beyond an agent-based configuration management tool, which is pretty critical, as you put it. But maybe I'm just hopelessly mired in the old ways of doing things, but even starting to approach that problem is just sort of a grand mystery to me. Like I try to think, well, how would I write a configuration management system that works across things? And it's just like, you might as well have asked me a question in Greek. I have no idea how to even start. So how do we start just sort of whittling away at that problem to make it manageable even?
So I think that containers help bridge that, first of all. So containers are already providing a way of making it easier to build those images that look the way that you want them to be. Now, I can't speak for Puppet and some of these other solutions quite yet, except for Chef, where the Chef team has been working on something called, actually I'm not sure if I'm supposed to say it, but I will, Chef Container and Chef and Knife Docker. So using Knife Docker, you can actually take your Chef recipes and use those to build a Docker file, which will build a Docker image. And that Docker image will actually has a mini agent in it. And that mini agent isn't really so much of an agent as it is basically a Chef-specific init. And that allows you to basically do last-minute configuration of that container. So this provides a bridge, right, to get from where we were before to where we are going tomorrow using Chef. I'm not aware yet of the other vendors providing similar solutions, but the paradigm of that and the model for that is similar. I also gave a talk at DevOps Days Pittsburgh about using configuration management with Docker, which goes over a lot of these things from a more, I guess, architectural model on how you would make your solutions work. Not necessarily using Knife Docker because it didn't exist yet. They announced it like the day after I gave that talk. But yeah, you can watch that talk, and I think it will help bridge some of that information.
So if I can just clarify real quick, it sounds like one thing that you're suggesting, which I'm sure has nothing to do with you working at Docker, would be that everyone just run Docker. Like everything, just like I run Docker on my phone and I run Docker on my Fitbit and everywhere. And so you would actually, and to me this seems pretty consistent with what we've been saying for a long time in configuration management, which is increase your homogeneity. Is that one way that, that we could approach this?
I think that we need to have one. I think that having one way of doing it is best. That has nothing to do with me working at Docker. I mean, Docker is one way of doing that where everything is the same and, you know, it already exists, right? You know, and this is one of the, it's more the other way around, right? This is one of the reasons I joined Docker rather than because I work at Docker.
Cool, thank you.
Hi. I was interested in the part early on when you were talking, the whole thing, but my question to do with when you were talking early on about embedded systems and tying that with what you were saying about how things will have to have sort of their own APIs so they can have I guess some intelligence in talking to, this is how I talk to this service, this is how I talk to that service. One of my friends does old school robotics, automation control systems ranging from TV trucks, you know, at big sporting events with walls of cameras to be managed, to turkey washing factories in North Carolina, et cetera, et cetera. And so much of what he works on is, you know, these are old systems, and it seems to me, and him, we've talked about it, there doesn't seem to be any hope for what you're talking about with controls, with configuration management of those where it was just never built with that in mind. And we don't really see what to do except for just eventually some things will wither away and be replaced. But, you know, he's working on systems that are 25 and 30 years old and have never been rebooted. You know, that's his reality. Right. And, you know, other than just, you know, well, eventually someone will put together a new turkey processing plant or something, you know, a whole new plant, because we don't really see the retrofit coming in. Sure. I'm just wondering, I know that's not quite exactly what you've been talking about, but it's such an interesting...
I think it's going to happen on both sides, right? Like, this disruption is occurring in two sides of our industry. One which is on the hardware and, you know, computer engineering, electrical engineering side, and the other side is happening in the software development world, and operations teams, operations management, which actually often is usually considered as two things already, right? So, like, you know, there are these like two very discrete fields, and each of these discrete fields has various different specializations within them, such as ops and developers, right? But then these two larger fields are coming together, and both of them are going to have to deal with the fact that they're going to have systems that they've built that don't do these things, that aren't built this way. That, you know, companies and services like, I mean, Amazon EC2, Salesforce, Gmail, I mean, everything, right? Like, everything that we have today, right? None of it is built this way. None of it is designed for this next generation, right? And I think that what's going to happen first is a lot of the things on the edges are going to do these things. A lot of these companies out of Shenzhen in China are going to build devices that are going to work this way. We're going to have a lot of startups in the US that are going to build, you know, the next big thing that's going to support this and use this. I mean, we may have some of the moderately larger companies like Facebook, you know, they may prove to be early adopters, right? Or some other companies might prove to be early adopters. I mean, Facebook has actually something they call Open Graph. So it's something not horribly dissimilar from this, because basically Facebook realized they need to solve these problems, but unfortunately they solved these problems for Facebook, right? And it's not, what they did is not necessarily a good solution for everybody. So, you know, they had a very web-centric view of it rather than a control and command and devices view of it. So I think that it's going to take you're right, it's going to take a long time before everything is this way, right? But I think just like with, you know, like, I feel like right now, it's almost like it's somewhere between 1989 and 1993, right, with the World Wide Web, right? That, like, we're just now thinking about it, we're just now starting to build it, we're just now starting to make it happen. And it's going to be a few more years before we have, you know, like, adoption of it, and then even more time before we actually have e-commerce, right?
Thank you.
No problem.
I actually had a question along kind of similar lines about the same point in the presentation when you started talking about managing things via, I guess, common APIs. I would love for that to be the case. I just don't think it's going to be. It seems like standardization of API calls, it would be a great thing that makes a lot of sense. But I have a kind of feeling that from a technical, political, institutional inertia perspective, that everybody who makes a light switch that's connected is going to have a different API, probably a radically different API.
Right. Yeah, so I agree that they're going to have, these things are going to have different APIs. It's a matter of defining what the protocol is to discovering that API, right? Like, if we had API discovery that was good enough that we could figure out that this thing is, first of all, a light switch, It doesn't matter, what the call to turn on and off that light switch is necessarily. That would already be better than what we have today. I mean, you're right. It's a tough problem. These are reasons that these problems haven't been solved. I think we're getting to a point where necessity is breeding innovation, whereas before, for a long time, these were academic problems, and we wanted to see these things happen because, oh, that would be really cool, but there wasn't a necessity, right? And now necessity is bringing that innovation, and I think that we as industry are going to figure it out and make it happen because we have to make it happen. And I think that we'll get over the challenges, but I think you're right. I mean, I don't think that it's going to be, every light switch is going to have this API. It's more like every light switch is going to have this protocol, and then it's going to use that protocol a little differently.
Okay. Well, I mean, even with protocols, you have protocols like SIP that are hyper-extensible, where the protocol becomes mushy past a certain point,
right?
Where it defines a certain core set, and then it's just so extensible that what does it really mean?
Sure.
So I'm kind of just curious how you would I don't know if you even have an answer to this, but how you would kind of overcome that problem.
Right. I mean, I've been looking at this for the last few months, spending a lot of my free time actually on this and trying to figure it out, right? And I don't have a canonical solution for you yet, right? Okay. I think that's, again, something that we care about now, so maybe we can figure it out. And there are companies that have been trying to do these things, but a lot of times, like API Blueprint, for instance, is trying to solve it from a documentation perspective and not from a semantic perspective, right? I mean, the whole semantic idea, right? We can have things like Waddle or another one's called JSON LD, I think, or JSON something. There's like another one of these JSON schema things. You can define what your API looks like. And we have to make these things easy to use so that people use them, simple enough that they use it correctly and they don't break it, right? They don't break their APIs. And we have to make sure that it actually enables something, right? And it's not just there for flavor. Because you're right that if we don't do it right, and if we don't figure out how to do this, then it doesn't really provide value. Right, because these things are still not going to be able to connect. A developer will be able to develop to it, but that's about it.
Right, you don't really get the advantages you get with a common DSL from like an agent, like Public
Right.
Chef. So, okay, great, thank you.